I didn't see is there. Oh. What? I don't know if this works. Hey, out of curiosity, can y'all hear me in the back, or do I need to figure out the microphone situation? Are we okay, or? All right. What was that? Yeah, I've never had to use it before though. So I don't know. Should I give it a shot? Do it. Okay. Feel. Does this work? System works. I don't know. Is this marginally better? I can't tell. Okay. Let's see. Is this marginally better? Can y'all hear me better up there? People that thought Mike would be. Is it not? Do I need to help me? Oh, you're fine. We're figuring out how it works. Yeah, you should be loud. You can totally reach that. No, I know. I thought it would be better. Totally, I agree. Friends in the back, is this better? Is the microphone like working? Yes, you. Is it not? Am I? No. Sadness. Evidently, they can hear you. Well, I know, but I don't want to have to strain my voice, friend. Okay, well, I can always just like hold on to it too. Oh, you think there's a distance? I don't know. I mean, test it. Slap it. No, it's on. Okay, it's clearly on. That's fine. There's a mic volume setting that you can probably just. Okay. Well, you don't want to like don't bring people here. Yeah. So I don't know how I don't like the old texting sound. Yeah, I guess. Test it. Maybe. I don't think it's substantially better. But if you talk at like normal words. What time we got? Okay, we still have 5 minutes. We're chilling. Well, I think it's directional. That sucks. So I think it matters which direction it's pointed. That up a bit higher, maybe. Dude, this is like as high as it's gonna go. I mean the zipper. What? You want like that? That way it doesn't like flop. If that's uncomfortable, don't do it. I don't know how mine's working. Neither do I. I'm not an audio engineer. Just usually working. Just talk loud. Okay. Anything else? Are we good? No, it's fine. Working. Do you have chalk? Director's working. I don't need chalk. Where we're going, we don't need chalk. Probably for like an example or something. If you want to elaborate. No, I don't think like there aren't really. This is just sort of conceptual. But there's plenty of questions. Put me over time. I'll put you on the spot. Ask you shit you don't know. Just like so in yesterday's paper. What's the voltage of pi? 4. 5. It depends if you're counting from 3 or 1. Oh, it was 5. I'm right. But it depends if you're counting from 3 is a digit. Oh no. Well, okay. All right. That's fine. Let's sit down in my gallery. Just annoying. You good? So. What? I've never presented that to this many people before, so.
Great. Have fun.
Yeah.
Enjoy.
But right,
That's the point.
I think so. I think that'll mean that I'm doing it right. I should set this clock.
I guess it's like there's gonna be something.
An hour.
And
Oh,
it's fun.
1 minute. My roommate Chris is helping me with audio.
Affiliated with
Verona's helping too.
simply
You want to sit with Verona? Yes. We don't know if this is like fully working. So. Appreciate it. Oh, yeah, it's a little nervous. Yeah. I'd be nervous if I wasn't nervous. So. Park wherever you want, dude. It's your world, man. Sit wherever you want. Sit on the desk facing the class like a, like a cool professor. Disappointing professor?
Yeah.
Oh, this is like cool. No, this is a cool professor. Is this a cool professor? Or I think it's a cool professor. If you're like,
Yeah, okay. I was picturing swap guys.
substitute.
That's what I have.
Substitutes are underpaid and overworked. I think you should have substitutes. Yeah, good subs. You're not substitute.
Or whoever was like in an adjacent office. That's it.
Yes. I wonder if it's. I know it's on. I wonder if it's directional. I think it's directional. Because if this feels like it's getting amplified.
Oh, nice. Oh, nice.
Yeah, it's fine. I have a timer on here, so it doesn't matter. I think it should be recording. Uh-huh. Oh, it's not up there. Perfect. He's not active in the club anymore. We can talk about Brian.
Nice.
Brian left. Verona touched these up last, so she should have her name on this.
Put it on there, right?
I don't think I can.
I'm kidding. I
I don't think, is this working? Hey,
How do you know it's recording?
because Zoom says it's recording right here. It says it
Oh,
right
it
here.
doesn't show.
Pause recording, stop
I
recording.
see. I was looking at there on one.
No one will ever
Is
know
anyone
this is
attending?
recorded.
Nope.
No, because it would be weird if someone did, because this is my own Zoom room. Someone's just sliding in my Zoom room. All right, I'm gonna start here. So, go be peanut gallery. All right, it's about 7:10. Y'all good to get started? Someone say no. All right. So welcome everyone. Thank you for being here. Welcome to CS 198-126, Deep Learning for Computer Vision. I'm Jake. Today I will be your lecturer. We have many other people on course staff. We'll introduce them in a little bit. But yeah, for the time being, thank you all for attending. I appreciate that you are here, and I'm really excited to teach y'all about deep learning and computer vision. So let's and the slides. There we go. So outline for today, meet our course staff, logistics, tell you a little bit about the course itself. And then we will get into the meat of today's lecture, which is just sort of a broad strokes overview about what is ML and how do we think about it. Course staff. More formal introduction. I am Jake. I'm a senior here at Berkeley. I'm computer science, somewhat obvious from the fact that I'm here teaching a computer science class. I'm mostly into computer vision, go figure, as is a lot of people on our course staff. We have Aryan, we have Verona, who is here today, Arvind, Rohan, and Ryan. These are people you'll see lecturing, as well as on EdSTEM, answering questions at homework parties, so on and so forth. So before we get into the course today or talk about logistics, I want to tell you a little bit about what this course is, why we're here, why I think this is an important class. So this is computer vision. The aim of this course is to be basically a boot camp into not only computer vision, but just deep learning for people who are freshmen, haven't had a chance to interact with the material before. Personally, I can say that when I was a freshman, it was really, really difficult for me to break into ML. It felt like clubs, courses, research were all off limits to me. And this is kind of my attempt to try and give back and hook people up with the resources that they would need in order to get a really good, positive first experience with ML and specifically with computer vision. The scope of this course is limited to computer vision with the intent to try and get as deep as possible and as close to, state of the art as possible. So you can see what it looks like, what the field actually looks like today. And this course is supposed to be, fun forward. I just want to make sure that's emphasized and out there and provide people a really good, positive first experience, because for a lot of people in this class, this is probably the first time you've seen deep learning. A lot of people in here are like freshmen, sophomores, they've taken 61A, Math 54, Math 53, whatever. And they want to know what it means for like computer science. So I just want y'all to know that this is supposed to be fun and a good time. And we really, really do hope that you have a good first interaction with machine learning here. So this is like just some fun stuff that this course will kind of go over. So at the top left, we have like a lot of more basic computer vision tasks, like classification. This is a cat. Where is the cat? Which is localization, localizing all kinds of objects, cats, dogs, ducks, and then showing where they are, what pixels correspond to cats, dogs, ducks, whatever. We're going to talk about how we learn from like large data sets of just images. How do we gain insights from that? Top right, we'll talk about masked auto-encoding a little bit later. Bottom left is 3D vision. 3D vision makes me really happy. How do we go from just different images of objects to like representing them? Neural radiance field is what that is. We'll learn a little bit more about that later. And then the bottom right, y'all maybe heard about DALL-E 2. That was just something off of like the MKBHD video on DALL-E 2, text-based image generation. And the prompt for this, I believe, was a bowl of soup that is a portal to another world. We will talk a little bit about generative art at the end. Hopefully that is intriguing, as intriguing to you as it is to me. So that's a flavor for the kinds of things we will be seeing throughout this course. So some quick logistics here. If you haven't seen already, hopefully y'all have, but this is our website, tiny URL, Fall 22 CV Decal. We have an EdSTEM. The slides are obviously, these are going to be linked on our website. I should have pointed that out. On our website, recording slides, assignments will all be posted. And so you can find these slides and find this EdSTEM link a little bit later. But EdSTEM is your way to interact with other students and the course staff. So this is a new course and there's going to be a lot of hiccups. We're going to screw up at some points. So this is where you let us know that like we've screwed up. And it's again, like a good chance for you to interact with the material, ask questions, talk to fellow students, that kind of stuff. Quizzes and assignments will be on Gradescope. This is the code. Again, you can find this later on the slides. The slides will be on the website. Classes Tuesday, Thursday, 8 to 7 p.m. Physics Building 2. Y'all are here, so good job. You got that one down. And enrollment codes have been sent out. Make sure you use them. Syllabus is on the website. It is the website, rather. So make sure to read it for a little more information. Does anyone have kinds of like questions here before we get started? Questions, comments, concerns? All right. Party on, party on. Feel free to interrupt me at any point or raise your hand and I will try and get to you. This is supposed to be fun and interactive. So, feel free to interact. Some announcements. The first quiz will be due at the end of next weekend. It'll be released a little bit later, either tonight or tomorrow on Gradescope. First assignment is in 2 weeks. Don't worry about it because it's not going to have anything to do with like the first 2 lectures. So y'all are chilling for a little while here. The first assignment will be short too, just pertaining to the tools that we use for deep learning. But it'll be released either later this week or next week. But again, it's short and you don't have to worry about it for a while here. So now for the first lecture. If anyone doesn't have any questions, then I'm gonna keep rolling on. All right. So again, this is meant to be an introductory course. Hopefully we get all the way up to state of the art. But this is for a lot of you, probably your first time using deep learning, and for many of you, probably your first time with ML. So again, this first lecture is really just supposed to be like, what is ML? So y'all get a flavor for like what we're trying to do here. So a little bit about ML. ML is just the paradigm of approximating data from approximating functions from our data. Traditionally, if you wanted to do a task, you would have to find a way to code up that task, make a function yourself, like in Python or whatever language you would choose. With ML, we're going to try and use our data to figure out what our function exactly does and what it looks like. Sort of a change in the traditional programming paradigm. So why would we want to do ML if we can just program things ourselves? Well, sometimes it's really, really hard to program things yourselves. So it's really easy to just learn from the data instead. We like to be lazy here. And that is the core of ML. How do we let our data guide our functions? So if you had a challenge of trying to classify this digit, it's a 7. If I asked you to write a program in Python to classify that digit, you would probably struggle. It's really, really hard to take in like an image and figure out what digit that is. I don't even know where we would start with that. If you wanted to try and program that, no, it's just not happening. It's much easier to try and find a way with ML to separate 7s from other values. And that's kind of like the flavor of the things that we're trying to tackle here with ML in general. How do we figure out what kind of function could separate this for us rather than trying to program one by hand? So let's narrow in a little bit on what ML is. It comes down to template creation at the end of the day. So rather than specifying some kind of function fully by hand, with ML, we're going to define the structure of the function, but leave a few parameters in there, which we will learn from the data that will determine exactly how our function behaves. For now, don't think too much about how we would go about learning these parameters, but I just want you to understand kind of like, again, what ML looks like. And in this case, it could look like something very simple, like on the right. We have a function that takes in an input and our parameter, A. It's very straightforward. If the input is greater than A, we return true, otherwise we return false. This is a function where A, in this case, is a parameter that we will learn. And it determines the way in which our function behaves. So that's sort of the idea, is we have a template of a function, and we will fill in the parameter values from our data. So in this case, let's think of like a one-dimensional line. We have red data and we have blue data. Our parameter is still A. If our input is less than A, we spit out the value red. Otherwise, we spit out the value blue. Again, this function is just like a hypothesized function. It's a template. We need to find a good value of A. That's going to work pretty well. We might suppose that the value 1 works pretty well. In this case, it does. If our input is less than 1, odds are, looking at this data, that it is red, and otherwise it is blue. So we hypothesized what our function kind of looks like, and we tried to find a good value of our parameters, in this case just A, that fit and spit out good values that we liked. However, if we change it very slightly and we just change the inequality so that if the input is greater than A, we return red, otherwise we return blue, there might be no values of our parameters that work well. And this is the important part of ML, is that what kinds of function templates we create really, really does determine how well our functions or our models can do. So it doesn't matter how cleverly you select your value of A, you can't get better than like 50% accuracy here. And it's just due to the fact that our model, our function here, is bad. It's not meant to do well on this data. So it's just important for you to note that the kind of function that you're using really does play a very big role in how good your results are. So being even more specific, the art of ML is simply figuring out what form our function takes, and this is sometimes referred to as like a class of model. And we're going to try and figure out, we're going to leave blank certain parts of this function. These are called parameters. These are values we're allowed to learn. And how we learn these values to, approximate the best possible values for this function. That is something we'll talk more about, but those are the basic 3 steps for like what is ML. Everything you'll see in this class, everything you might see in other classes, whether that's CS 182, CS 189, CS 188, or graduate level classes, whatever, it literally, this is all it is. What is the template for your function? What values of that function are we allowed to learn? And how do we go about learning those values? So it's literally just template creation. Does anyone have questions at this point? Because this is for people that are new to ML. This is probably still slightly nebulous, and you probably might have questions at this point. So if any have questions, feel free to raise your hand, ask. You're expected to still be, again, somewhat in the dark on this. We're going to talk more about specific kinds of models, which parameters are learnable, and how we go about learning them more in the future. Yeah, but for now, this is the broad idea, if you haven't seen ML before, of what we're trying to do. So if there are no questions, I will keep on trucking. So how do we describe all of the different kinds of ML? It's useful to kind of like categorize things. We really have a broad definition of what ML is, and now we want to try and like break that up a little bit more into the different kinds of tasks that we might be doing. So in ML, we have supervised learning, which is like classification, like figuring out whether that image is a 7 or a 1 or a 2 or a 3 or whatever. Or regression, which you may be seeing in like stats or something like that. We have unsupervised learning, which is how do we learn insights from just swaths of just unlabeled data. Like our images with digits, had labels on them. Like we could tell clearly that that's a 7, and we could label it as a 7. What happens if we don't have labels like that and we just want to learn from data in general? That's unsupervised learning. We'll touch a little bit more on that later in this course. And then reinforcement learning is something we're not going to talk about at all in this course, but it's how do we react to environments that we don't fully understand. So that's sort of the taxonomy of ML, so to speak. So a little bit of vocab before we keep on going. Function or model, these are terms that are used interchangeably. It's again just a template with some parameters that we're going to try and learn the best values for. Parameters, weights, and biases. These are all just interchangeable terms for parameters. Weights and biases are terms that specifically arose from deep learning. Weights are things that are multiplying other values, and biases are things that are generally being added. But they're all parameters, and they're all things that are learned. A hyperparameter is like a non-learned parameter. It refers to things like how big our model is, what class of model we have chosen to use in the first place, the training procedure. These are things that aren't learned. I don't know how you would go about learning which training procedure, which learning algorithm you would use. That's an insane task. These are just things we set ahead of time, like setting what do we want our function to look like. We have loss function, cost function, risk function. These will come up a little bit later. They're all just interchangeable. You might hear them get tossed around. And we have feature, and this just refers to bits of data. They're either inputs or representations of our data that we've learned. So you'll see all of these getting tossed around. Does anyone have clarifications on the vocab before we move forward? Yeah, we got. No, well, you have just like a whole bunch of data. So like imagine we just have like a whole bunch of images and we don't attach labels. So like we just have a data set of just images and we don't have labels. And it's like, how do we learn from that? How can we do interesting things with this data still? Does that kind of make sense? Okay. Whereas supervised learning is when we have the labels attached and our computer can say like, this is a 7. not from the image, but from a label that we've attached to it. Yeah, what do we got?
So in this case, the model will classify all of the images on like its own logic, and then we assign labels to them.
In supervised learning, or in unsupervised, yeah, sorry. In unsupervised learning, yeah, that could be a task. Is say we have a whole bunch of images and we want to like, we don't necessarily like, say we want to cluster them as a frequent one. So like we have just a whole bunch of images, and can we find some groupings of them that are like similar? So yeah, and frequently we'll talk a little bit more about this down the line, but you can use, actually, no, I'm not even gonna, sorry. But does that sort of make sense? Like things you can do with unsupervised learning? Yeah, there's a lot of other things we'll talk about too with unsupervised learning. But hopefully that gets you to understand what the whole deal with unsupervised learning is. Anyone else have questions on like vocab and stuff? All right, party on. So let's talk a little about the ML pipeline. So the process of actually doing ML, it's pretty straightforward. We're going to figure out like what our problem is. This is sort of like a project management level, figuring out what our problem is. What are we trying to solve? We got to prepare the data, get it ready, and make sure that it is usable for whatever model we're going to be using down the line. And then we pick our model, our loss function, which is what are we going to be trying to like optimize for, and then train it, minimize our loss function, optimize our model, and then that's it. So let's go into this a little bit more. Defining the problem, this is very much just like a project management thing, but just like, what does your data look like? What are you trying to do? And what is your metric for success on like a project level? Like, what do you want this to do? These are just things you need to figure out. Hopefully these are somewhat obvious, but it's important that you have like an understanding of what you're trying to do when you go into any ML project. Preparing your data. So you have to collect your data. Don't take this for granted, because like seriously, in the real world, it can be really hard to find, especially for computer vision, like the right kind of data set that you want. And if you have really crummy data, your model is going to learn really crummy things. Garbage in equals garbage out. Don't take this for granted. We're going to have hopefully good data for you in the course. We're going to be using like data sets that are widely used in research. But in general, for your own projects, this is like so important. Don't take it for granted, the existence of good data that is labeled. Yeah, we need to find a way to represent our data with numbers. All of this is just math at the end of the day. Our functions are just templates, but it's still math. So we need to figure out how to convert everything into numbers. If we have text, we got to get it into numbers. Image files need to be represented by numbers. Every single data point, it's got to be numbers. You have to select which parts of your data are important, which parts of our data do we want to use as input to our function. And we sometimes do things like normalization to make sure that our features are like all about the same quantity. You'll see this more down the line. It's just something to keep in mind, that our features should be like on the same scale. And frequently we just put everything in vectors. We just take all of our important numbers and just string them up into a vector. That's like mission critical that you understand that too. Vectorization of our data. Just take everything that's important, plop it in a vector. Yeah, and make sure that the order stays the same. Otherwise it's chaos. So representing labels. One hot labeling. This is getting a little bit ahead of myself. However, it's still like important to know, and it's a good chance to think about how we go about representing data. One hot labeling is the most common labeling scheme. So before we had images, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And how do we like label that? Because our labels too need to be represented as numbers. And sometimes it's really difficult if we just put the label as the number 4. Frequently, it's really best practice to represent the number 4 as follows: 4 zeros followed by a 1, followed by as many more zeros as we have labels. Having one unique digit output for all of our potential different outputs that we want our model to be able to recognize. So one hot labeling, just to sum it up, is simply a vector of zeros with a 1 in the position corresponding to what kind of data that is. So again, if we have just a vector if we have, for classifying digits, 0, 1, 2, 3, whatever. Our labels in this case for an image with the number 3 in it, 0 indexing would be for the image 0. That corresponds to the first spot in our label, 0, 0, 1, as this is the third spot, followed by 6 more zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 different outputs, or 10 different kinds of data, 10 different kinds of images. And we have one spot for each of them. If our image is a 3, we're going to plop a 1 in that spot. This is something that's useful more down the line, but it's just important to think about. So if we're trying to classify, if our model isn't sure, say it gets something that looks kind of like maybe like that. Like, is this a 7 or is it a 2? Maybe it's ideal that our model says, I'm not really sure. 50-50, I'm kind of split between whether that's a 7 or a 2. I don't know. And then what should we do in that case? What do we want our model to output? Like, would we want our model to output 4.5? Because that's the middle between 7 and 2. But wait, that's not 4.5. That's clearly messed up. That's not right. So rather than that, it's probably better that our model just says, you know what? I think 50-50 probability, that's a 2. And then 50-50 probability, that's a 7. It allows us to be more expressive about what our data is, what we're representing. So that's kind of an important point, and it's a little bit maybe confusing. So does anyone have questions on that? Because yeah, one-hot labeling is something we'll see a lot.
Is there like a particular reason why the 0 index is not used at all?
This guy?
Yeah.
Oh,
Or is
well,
that used for the digit 0?
oh no, it would be.
Oh, okay.
Yeah. So if we had the image 0 right here, that would correspond to just 1 followed by all zeros. Yeah, sorry, maybe that was a little bit confusing. Is everyone okay with that? Any questions, comments, concerns? All right. Yeah, so that's getting ahead of myself, but the important point here really is that it's important to think about what our data looks like and to make sure that it can be interpreted correctly. Representation of data is, like, again, mission critical, because without that, it's madness. So defining a model and defining a loss function. So we're going to talk a lot about different kinds of models, so don't worry about that now. Just kind of black box it for now. So we want to know, again, as we talked about before, like, what is our template that we're going to be filling in with parameters that we're going to be learning? What kind of model do we want to use? That is a function of what kind of problem this is. What do our inputs look like? What do our outputs look like? Thinking about what kind of model to use requires you to think about, again, what kind of problem this is, what does our data look like, all that kind of stuff. Again, we will learn more about this, so don't worry too much if you can't think of an explicit model at the moment. We can also try different models and just see which one works better. That's something we'll talk about more down the line. So yeah, that's defining a model, defining a function needs to be done. And remember, we need to, like, optimize this. We need to figure out, like, what settings of our parameter are best. But in order to figure that out, we need to know what we want. If we have no concept of, like, what we're aiming for, like what metric we're trying to optimize, like, we're screwed. Like, we can't even start. So different models will have different ways to optimize for the parameters, but all of them need some kind of goal, some kind of metric that we're going to optimize for. And this is what our loss function is basically. Once you have the model, once you have your data, your job is going to be to minimize this loss function. And the reason we call it a loss function is it's a value that if it's high, that generally means our parameters are kind of bad, they could be better. And if we have low loss, that means we have good parameters. It is our metric for success to have low loss. And you need to make sure that whatever your objective is corresponds to a loss function that is low. So in supervised learning, before we were talking about, again, like labeled digits. If we, in this case, wanted low loss, we might want our model's outputs, which will just be, again, in one hot format, we might want them to match the correct label given an input image. So given a 3, we really want to make sure that our model is spitting out something that looks like this, a one hot vector with a 1 in the 3's position. And to do that, you can just take like the mean squared error. Just say like if our model is like, you know, say it's doing like 0.8, like 0.2, it's like 80% sure that we have a 3 and 20% sure that it's a 4. Mean squared error, if we just look at the correct label, which has a 1 in the 3's position and a 0 in the 4's position, we just take the distance between our correct label and our model's output. That is a single value that we can optimize for, just a single number that represents how good our model's doing. If our error between our labels and our model's output is really high, then our loss is really high and we need to be doing a better job. And if it's really low, we're doing a good job. So it's a single value. Mean squared error is just an example of a function that's just taking the distance between our model's outputs and our correct outputs. And it just is a single value, a loss function that scores how well we're doing. We'll talk more about that later. So if you didn't get that, that's okay. But just again, the idea that I really want to make sure I'm conveying is that we want some kind of metric to optimize for. Does anyone have questions, comments, concerns? Yes, friend?
Yeah, is the loss function something you like derive or something you choose for your model?
Oh yeah, you choose it. Yeah, it's another like hyperparameter. It's something we choose. There's all different kinds of loss functions you can choose that make sure that our model's output like is really close to our labels. Mean squared error is just like really easy to write. So that's frequently why it's like brought up first. Yeah, it's something we're gonna choose before we go into it. Because again, we want to make sure we have like an idea of what we're trying to optimize. So our loss function is just that metric for what we're trying to optimize. So yeah, it's something we're going to choose beforehand. So training, this is something, again, we haven't talked about models yet, so we can't really talk about training procedures. But once we have the data, the model, the loss function, we just have to use some algorithm to figure out which values of the parameters in our function are optimal, which ones are giving us good outputs according to our loss function. We'll cover these more later, but the hope is that you sort of, yeah, you'll get a flavor for this more down the line. But the understanding I want you to take away here is that training is the phase where we're going to just select the good values of the parameters that mean our model outputs really good values. And then finishing up an ML project. Use some testing set that our model has never seen before, some set of data, so that you can report your results. And frequently you can use this to see how you stack up to other systems, like state-of-the-art systems. So you can use, if you have your model and you want to see how well it's doing, you can use a common data set like MNIST. We saw those digits earlier. It's from MNIST. And you can see how well your model, your training procedure, your loss function stack up. And it's the way that we standardize, our results across ML and check and make sure that, we're moving the ball forward, everything. So yeah. Questions, comments, concerns before we jump on to another topic? All right. So let's talk a little bit about generalization. So we've just seen performance on training and testing data. How well our model generalizes is simply how well we're doing on the data that we were training on versus how well we're doing on new data. Because really at the end of the day, if our functions can't, or if our models can't do well on data we haven't seen before, all of this means nothing. We want to make sure that in the real world on data that we've never seen before, we can still do a good job. If we make our model more complex, we might find that it's really good at like memorizing the data. And that's not what we want, because then when we see new stuff, it's not going to know what to do because all it did was just memorize all of our training data. So you want to make sure that you're not doing well just on the data you've trained on, but you want to make sure you're doing well on data you've never seen before. So with that in mind, we're going to talk a little bit about bias variance. Or does anyone have questions on the idea of generalization, what we're trying to accomplish. All right. So bias variance. This is something that you're going to run into not just in deep learning, but everywhere in ML. 182, 189, every class you're going to take on ML. When you're talking about things that are learned, there's always this bias variance trade-off. On one hand, we have bias, which is just our model's tendency towards certain predictions. Normally, when we have really low complexity models that aren't super expressive, they're going to just generally bias towards certain values. They're not very good at learning. Small changes in our data set means our model's still going to be off by that same amount, and our predictions are still going to be off by some amount. And on the other hand, we have variance. If our model is really good and can just like memorize all the data, we're going to find that if we're too good at matching our data, then we're generally not going to be able to generalize very well. We're not going to do very well on new data we haven't seen before. And this is generally seen when you have small changes in your data set that result in wild changes to your model and how it behaves. It basically comes down to that we want our model to be able to capture the complexities in our data, but we still want to make sure that it's robust if our data set changes slightly, or if the kinds of things we've seen when we train vary slightly. We don't want to just memorize our data. We want to make sure we're learning meaningful patterns about it. And this is sort of like a really good example, in my opinion. So the green polynomial or sine function is where our data came from. And we added a little bit of noise to it in blue. And that is our data set that we're training on. And our model in this case is just a different kind of polynomial. On the top left, it's just a polynomial, a 0-degree polynomial, effectively. That's just a constant. It's super high bias. It's not matching our data at all. It's biasing towards certain values. And it doesn't matter whether our data is noisy or not. It's still going to do really bad. It's just biasing towards the constant value. On the top right, maybe getting a little bit better. We're now learning a line. It's a step up. Still kind of high bias. Doesn't matter whether our data changes. We're still going to predict about that same line. We're still going to bias towards certain values. And on the bottom left, that's sort of the golden zone. You know, our model is as complex as our data was, and we're fitting pretty well. If our data becomes slightly more noisy, we're still probably going to do pretty well. But you know, we're not necessarily biasing towards bad values. We're in the Goldilocks zone. And then on the right, our model is way more complex than our data. You can see on the edges, our predicted red polynomial is just wilding out. Its values are insane and don't correspond to our data. And the reason that happens is because we're perfectly able to fit to the noise. Look, we're going through those blue points. We're not just going near them, we're going through them. But that causes everything in between, all of our predictions in between, to just be wild. In order to accommodate that noise in the data, our predictions, everything in between, everything we haven't seen before is just going to be garbage. So that's that sort of trade-off. And this is something you will see often. If your model is way more complex than your data set, you might just overfit and not do very well on new data. This is the bias variance trade-off. This is pretty much core to ML. You're going to see this everywhere you go. And hopefully you have a little bit of a flavor for what that looks like at this point in time. Does anyone have questions? Because this is like a really important concept. Questions, comments, concerns? Yes, friend?
So what is the bias and the variance in these examples?
Yeah, so the bias, again, in our top left example, it's biased towards just one value. It's just a constant, right? Like, it doesn't matter what we put in, like, we're always going to be off. We're always going to be spitting out, you know, just a constant value. We're biased towards certain values. And variance, again, generally refers to, like on the last slide, if we change our data set slightly, because we're overfitting so much to this data, we're trying to match it so much in order to minimize our loss, that, you know, we end up having wild and erratic behavior for values that we haven't actually, seen before. Does that kind of make sense?
Yeah.
There's like a more mathematical way to do it, but I didn't want to do that. I don't want to scare y'all off. But it basically corresponds to how much your model is able to match the data. If your model is able to match the data too much, like in the bottom right-hand corner, we have no error from our blue points that we're, training our model on, that we're fitting on. We have no error, but that still means we're not doing a good job, right? Because it's clear that everything that we've never seen before is still just like insanity. We tried so hard to match the blue data that we ended up shooting ourselves in the foot and our model was trash. And on the left-hand side, you can see it's that sort of Goldilocks zone between we're fitting to the data accurately. We're not perfect. It's not exactly going to the blue points, but it's getting the gist of it, and it's sort of learning the core, pattern in that data. Does that make a little more sense? Okay. Anyone have more questions, comments, concerns? Yes, friend. Yeah. So the loss function is, so say we've chosen polynomial. So say we've chosen like a degree 3 polynomial, and we've chosen a loss function, which is just like how far is the red line from like the blue dots. Our loss function is what's going to tell us what all the coefficients of our polynomial are that are going to define the shape of that polynomial. Picking which polynomial is referred to like hyperparameter tuning, because the degree of our polynomial is a hyperparameter. It's not something that we learn ahead of time, and you're gonna have to. It's gonna just end up being trial and error, to be honest. Hyperparameter tuning is difficult, and it generally involves holding out, a segment of your data. You have your training data and you have your testing data. You're going to train a model, and you're going to see how well it generalizes. And you're going to try and look for a class of model that is going to, a selection of your hyperparameters that's going to generalize well to your new data. Does that make a little more sense? Yeah, so your loss function corresponds to actually training the model once you have selected what it looks like. Yeah. So overfitting and underfitting. I think I might have accidentally used the words earlier in trying to explain this stuff. But it just sort of explicitly says, thing we care about is generalization. We want to hold out a little bit of our data. I realize I jumped the gun there on the last slide. We want to hold out a little bit of our data to test and see how well we're doing on values we've never seen before. What we really care about, well, we do care about, the full accuracy to some degree. But another thing that we really care about is the difference between the accuracy on the data that we trained on and the accuracy on data that we've never seen before. Because again, it's really important that on new data, like if we're deploying a system in the real world, it's really important that our model is able to generalize, because in the real world, you're going to be seeing data that you've never seen before, that you never trained on. And if you can't do well in that data, then it's really bad situation. So this is again the balance between bias and variance. If we're overfitting, then our model's way too complex. We have a lot of variance, and we need to scale things down and find ways to make it less complex. Sorry, and make sure that we can't just memorize our data blindly. Like we can't just intersect with every blue point exactly and get like zero loss. We don't want to overfit like that. And on the other hand, we don't want to underfit. We don't want to just get a line with like a crazy amount of bias. That's not helpful either. We need a happy medium. It's a trade-off between being able to have a model that's complex enough to capture all of these rich patterns in our data, and having a model that is still robust enough to generalize. And again, we're going to have to try a lot of different models. We're going to have to try a lot of different models, play around with our hyperparameters until we find something that works pretty well and doesn't have a huge discrepancy between data that we trained our model on and data that we're now testing on that we've never seen before. So wrapping up, does anyone have questions before I try and cap things off? Questions, comments, concerns? Yes, friend.
So it's like bias, how good you do on training set, and variance, how good you do on like test set, or
Your bias, generally models that have really high bias will have very close accuracies between your training and testing data, because it doesn't matter what you feed into the model, it's always going to spit out the same thing, right? Yeah, if our model always spits out like, you know, the value 1 for some input value X, it's going to do the exact same thing on training and testing data. So it's going to have about the same error there. And variance is, again, fitting too much to the data, so that we have our loss here, the distance between the red and the blue points is nothing. And we were able to do that by just memorizing the data. So that's again the sort of idea of variance. And generally, when we test on values that are, you know, in between our blue points in our training set, when we test on new points, we're going to get huge loss. And that's, you know, so generally when you see a system that is, there's a huge gap in between our training and testing error, our training and testing loss, that's generally a sign of high variance. Whereas if we're getting really trash accuracy, but our model is doing about the same on training and testing data, that's generally an indicator of high bias. Does everyone feel okay with that? Awesome. So wrapping up today's lecture, where are we on time? Ooh, golden. So the important things I wanted you to take away from this, because again, like this is meant to be like a really introductory course, not just to deep learning or computer vision, but also to like ML. And I want to make sure y'all kind of have a feel for what we're trying to do here. ML is just template creation. You know, we just created some Python function with some empty value A, and we're going to need to use our data to try and fill in that value. It just comes down to template creation. And in ML, you define the problem. You got to prep your data, make sure it is expressive enough, as we talked about, like one-hot vectors. We need to make sure that it's clean, that it's usable, that we can actually like learn stuff from it. You need to define what kind of model you're using, the loss function, all your hyperparameters, choose them, and then train the model. And I also want to make sure you understand that there's this trade-off, and you're going to see this a lot, especially in deep learning. There's this huge trade-off between the complexity of your model and how well you're able to generalize. And this is the bias variance trade-off. You're going to see this pretty much straight off the bat as soon as you start training models. So I want to have you, I hope you have somewhat of a flavor for that idea between complexity and our ability to just memorize our data versus our ability to, you know, be robust and generalize. So yeah, does anyone have questions, comments, concerns? All right. I think that about wraps it up for today. Thank y'all for coming out here. I appreciate your time. I hope you have a good time in this class. I will be down here if you want to come down and chat it up. I can explain things a little bit better, maybe. Yes, friend. It's not, but it's really better if you show up, friend. I really enjoy it more. This is, I should actually, before y'all leave, I want to just emphasize here, like, I'm fully aware that this is a decal. This is not your priority and should not be your priority. So this is hopefully we're giving you the resources you need to learn about machine learning and deep learning. But if you don't want to, you know, put in the work, I can't stop you. I'm not here to hand out NPs like candy. I want y'all to pass, but please show up. Again, like, this is my effort to try and like give back and make sure that there's openings for people to like get into ML and get into deep learning, because I think this is really cool, and I think y'all should too. So attendance isn't taken, but like, show up, please. Thank you, friend. Yay, Val.